Hi everyone, in this recording we will be going over the trigonometric form of a complex number. Our goal is that by the end of this presentation you'll be able to write trigonometric forms of complex numbers, you'll be able to multiply and divide those complex numbers when written in trigonometric form, that you'll be able to use de Moivre's theorem to find powers of complex numbers, and that you'll be able to find the nth roots of complex numbers. The trigonometric form for the complex number z is given by this formula right here. So the x, or the horizontal portion, the real portion, is equal to r times cosine of theta, and the imaginary portion is equal to sine of theta. So then that means, r times sine of theta. So that means our complex number z is equal to bi is equal to r times cosine of theta plus I times sine of theta. And then we have tangent of theta is equal to b divided by a. So the imaginary portion divided by the real portion. So if we let theta be the angle from the positive real axis and counterclockwise to the line of the segment that connects the origin, and the point AB, the complex number a plus bi on the complex plane. So we can write a is equal to r times cosine of theta, the real portion, and b is equal to r times sine of theta, the imaginary portion. Then the distance from the point AB to the origin is equal to the square root of a squared plus b squared, and that is r. So as a result, we obtain that a plus bi is equal to r times cosine of theta plus r times sine of theta I, where r is a modulus, or the absolute value of z, and theta is the argument of z. The trigonometric form of a complex number is also known as its polar form. So in other problems, the interval of theta is restricted to theta being greater than or equal to 0 and less than 2 pi, but in polar form, sometimes it is more convenient to work with theta less than 0. So in this example, we are solving for the trigonometric form of the complex number 1 plus I. So first we need to find r, our modulus, so that'll be the square root of the sum of the squares of each of the real and the imaginary components. So for our real portion we have 1, and the imaginary portion we have 1, so we'll have 1 squared plus 1 squared, so then we'll have 2, and r is equal to the square root of 2. Now our second step is to find the angle. So because the horizontal distance 1 and the vertical distance 1 are exactly equal, then the angle forms a perfect split down the middle of the quadrant. So that means that our angle is at exactly 45 degrees, or at pi over 4 radians. So now we can write our final answer. We can substitute our distance, the square root of 2, and our angle, 45 degrees. So our complex number in the trig form will be the square root of 2 times the cosine of 45 degrees plus I sine of 45 degrees. So now the product of two complex numbers is defined as, so we multiply the modulus of z1 and z2, so r1 and r2, times, now for the horizontal component, we add the angles, so we'll have cosine of theta 1 plus theta 2, plus, now in the vertical component, we'll do sine of theta 1 plus theta 2. Now for the quotient of two complex numbers, we divide their modulus, so r1 divided by r2, times, and then in the horizontal component, we will subtract the angles, so cosine of theta 1 minus theta 2, plus I sine, and then in the vertical component we will subtract the angles once again, so sine of theta 1 minus theta 2. So here z1 is our first complex number corresponding to r1 times cosine of theta 1 plus I sine of theta 1, and z2 is equal to r2 times cosine of theta 2 plus I sine of theta 2. Now here are some examples of what we just defined. So we're told to divide the two complex numbers 6 times cosine of 70 degrees plus I times sine of 70 degrees by 2 times cosine of 30 degrees plus I times sine of 30 degrees. So for division, we subtract the angles, so we'll be doing cosine of 70 degrees minus 30 degrees, so that would be cosine of 40 degrees, and sine of 70 degrees minus 30 degrees, so that'll be sine of 40 degrees. Now we divide the modulus, so each of the respective lengths, so we'll do 6 divided by 2, and that is equal to 3. Now we could just multiply 3 by the cosine of 40 and the sine of 40 degrees, I, don't forget the I, And then this is our final answer, 3 times the cosine of 40 degrees plus I sine of 40 degrees. So now for multiplication, we add the angles. So for the first complex number, we have 3 times cosine of 20 degrees plus I sine of 20 degrees. And make sure that the 3 is on the outside of the parentheses so that it is distributed to both the horizontal and the vertical components. And then for the second complex numbers, we have 2 times cosine of 45 degrees plus I sine of 45 degrees. So for the angles, we will have 20 plus 45, and that is equal to 65 degrees. Now we can multiply the lengths, so that's 3 times 2. So that means that the product of these two complex numbers is equal to 6 times cosine of 65 degrees plus I times sine of 65 degrees. So if you want to raise a complex number to a power, you can use a trigonometric form of complex numbers. So first we write it in the trig form, so we do the length, well first for the complex number z, we write it as the length times the cosine of theta plus the vertical composition, so I times sine of theta. So then for z squared, that is equivalent to saying r times r for the length, and then since we're multiplying, we add the angles, so theta plus theta. So r times r is r squared, and then theta plus theta is equivalent to 2 theta. So now for z squared, we have r squared times cosine of 2 theta plus I times sine of 2 theta. Now for z cubed, that is equivalent to saying r squared times r, so that gives us r cubed, and we are adding the 3 angles, so theta plus theta plus theta, so that's 3 theta, so repetitive addition. So r cubed times cosine of 3 theta plus I times sine of 3 theta for z cubed. So this pattern leads to what the French mathematician Abraham de Moivre states. So for de Moivre's theorem, we have that if we have a complex number z is equal to r times cosine of theta plus I times sine of theta, and n is a positive integer, then if we raise that complex number to the power of n, that is equivalent to r to the power of n times cosine of n theta plus I times sine of n theta. Now here's us practicing that theorem. So if we want to raise z1 to the second power, where z1 is equal to 3 times cosine of 40 degrees plus I times sine of 40 degrees. So first we raise the length to the nth power, so we're squaring it, so 3 times 3 is equal to 9. Now we multiply the angle by the power, so our power was 2, so 40 degrees times 2 is equal to 80 degrees. So then our final answer is 9 times cosine of 80 degrees plus I times sine of 80 degrees. So for the definition of an nth root of a complex number, we're given that the complex number u is equal to a plus bi is an nth root of the complex number z when z is equal to u to the power of n, and we just substitute a plus bi for u and raise that to the power of n. So finding the nth roots of a complex number, for a positive integer n, the complex number z is equal to the length r times the cosine of theta plus I times the sine of theta has exactly n distinct nth roots given by this equation. So z with a subscript k, where k is equal to 0, 1, 2, up until n minus 1, is equal to the nth root of r times cosine of theta plus 2 pi k divided by n plus I times sine of theta plus 2 pi k divided by n. So to find the 6 complex solutions to the polynomial equation x to the power of 6 is equal to 1, we can rearrange the equation x to the power of 6 minus 1 and set that equal to 0. We can use a combination of factoring techniques, so the difference of squares and cubes, along with the quadratic formula. So first we move the 1 to the left hand side, so we subtract on both sides. So now we have x to the power of 6 minus 1 is equal to 0. Now that is the difference of squares. So x to the power of 6 minus 1 is equivalent to x to the power of 3 minus 1 times x to the power of 3 plus 1. Now using the difference of cubes, x cubed minus 1 is equivalent to x minus 1 times x squared plus x plus 1, and x cubed plus 1 is equivalent to x plus 1 times x squared minus x plus 1, and all of that set equal to 0. So now we have x minus 1 set equal to 0 implies that x is equal to positive 1, and x plus 1 set equal to 0 implies that x is equal to negative 1. And now for the two quadratic or the two polynomials, we can use a quadratic formula, and we'll get that x is equal to -1 plus or minus the square root of 3i divided by 2, and x is equal to 1 plus or minus the square root of 3i divided by 2. So here we're finding the 3 cube roots of the number 8. So the number 8 falls flat on the real axis because there's no imaginary portion. So we can write 8 in its trigonometric form. So that is equal to 8 times the cosine of 0 degrees plus I times the sine of 0 degrees. So we find the length of the roots. So every single root will be exactly 2 units long because the cube root of 8 is equal to 2. Now we slice up the circle, we find the angles, so we divide by 3 since we're looking for the 3 cube roots. So 360 degrees divided by 3 gives us 120 degrees. So now we can write the 3 roots. So for root 1, we have length 2 at 0 degrees, so 2 times cosine of 0 plus I times sine of 0. Now for root 2, we have 2 times cosine of 120 degrees plus I sine of 120 degrees. And lastly, for root 3, we have 2 times cosine of 240 degrees plus I times the sine of 240 degrees. So we just added by increments of 120 for the degrees since we divided the 360 by 3 and got 120.